Yeah, I'm ready when you are.
Okay. I'll start with just a few news about Gazebo, but then we can move to your presentation.
And
And
Yeah, sure.
we're good to go. Recordings are going live.
all right. Hello, everybody. Welcome to the April Gazebo community meeting. Let me start by sharing the screen with the agenda for today. We're going to start, as usual, with some Gazebo news, and then we have the pleasure to have a presentation from Antar Mazumder. He's going to talk about Antar about how to create digital elevation models in using different simulations, including Gazebo, uh, using 2D images. That's my understanding, but he'll go into all the details for sure. And as usual, there's time for questions. So we can start with some of the updates. I have some slides here uh, that I used a couple of days ago that I think are very handy for today. So things are happening in the last month. One of the items that's has been complete and it's in the roadmap. It's the migration from Qt5 to Qt6. So kudos to Ian that is here, I believe. Yeah, who continue and finished most of the work that started at ISU mainly. And you can see here the main issue that we use to track some of the progress. And as I said, I'd say most of the migration is complete. Um, these are the two main PRs, although there are other minor PRs also that has been merged, many of them actually. And CI tasks to make sure that we are green have been also merged, and most of the stuff is complete except the minor issues that have been detected after merging everything, and they are already tracked. So very good news. Next one is the update to use Xeno in GC transport. Same thing. So this is the issue that you can see if you have interest, where we track some of the progress. Next is the design document that we use as a guide for working on the integration. And one of the decisions that we made in one of the PMC meetings was to support Serum Q and Xeno at runtime. So, and the idea is just to install just the regular package as usual, GC transport, or compile it from source, just one package, and have both versions available. Of course, if you install the Xeno dependencies. The Xeno dependency is going to be optional, so you have the ability to keep using it as it was without forcing you to install the Xeno dependency. There's going to be an environment variable similar to what happens in the RMW Xeno. It's going to be GC transport, GC underscore transport underscore implementation, and then we should be able to set that to 0MQ or Xeno, and um, and yeah, and that's how you will choose the underlying middleware that you want. There are three parts already under review. The first one just mostly CMake stuff to make sure that the dependencies are found, and if they are found, enable the code that has Xeno, otherwise just only the 0Q, basic PubSub, basic asynchronous services, and there's also additional work that has been started and it's ongoing for having support for CI when working with Xeno and all these PRs that we are starting to create. Another item that's on the roadmap is the use binaries instead of shared libraries for the command line. So this is also an effort that Shrap and Jose are leading. Um, there are a bunch of issues that you can also check to track the progress of this issue. And I'd say that development is also very advanced. There were a few tests that we were doing on Mac, and there's an open PR already to start the process. We just need to fix a few tests, and I think Sorab is just going to add some extra code on top of that PR. So he's going to create another PR, but it's looking very good. So I think we're on track for this one in the roadmap. And then there are other updates, some of them related with infrastructure. There's this ongoing effort that we want to try, which is maybe in the long, we call it auto release, the Gazebo leaps. Maybe this is the optimistic or the wish goal, but the idea is just to reduce the friction when we make releases. And maybe the end goal is just that we don't have to do anything, and then releases are going to be happening automatically every, let's say, 2 weeks in each of our libraries. But for doing that, we need to solve a few steps in the road, and some of them are related with the changelog. So how do we deal with the changelog? The idea for now is going to be that every PR includes the changelog. You know, this thing has a few drawbacks, like for example, it's going to be very easy that 2 PRs open have conflicts on the same file with the changelog. So we have a few ideas here and there, and this is a process that we pretty much started. There's a document that tracks the ideas, and the changelog step is maybe the first one that has been moved a little bit with some of the ideas. Content migration has been pretty much complete, and also the build Foundation.org has been scaled down during the weekends in an effort to reduce costs in our build farm. There's also an effort led by Steve Peters and also RoSE for removing version numbers from package names. It's been ongoing, and we have implemented the plan in some of the libraries. This is Sim, GC Transport, GC Sensors, and then in the last PMC meeting or 2 weeks ago, we decided that we're going to try it out in all the libraries. We prefer not to have like an intermediate step where some of the libraries don't have version numbers and the others do. So I think we're very happy with the results so far. So we are in this path of forward porting everything and then doing the steps that we need to do to remove that in all the libraries. There's also the contributor recruiting program, thanks to Kat. We're very happy with the results. So the idea is that we're going to try to remove the version number when we do, in Python ideally, and also when we do in our CMakes and etc. We're not gonna have version numbers, so moving from one version to the next one is gonna be very easy, and as opposed to right now that we have to bump and change all the major numbers every time that we change versions. I was talking about the recruiting program, so the contributor recruiting program, the very, very successful program. We encourage everybody to participate. If you're interested in, maybe you haven't done it yet, but you're interested in maybe getting familiar with Gazebo. So we are trying to create a set of issues that are a little bit more curated, a little bit more guided, and maybe for helping you to start contributing to Gazebo. We're going to try something also new, which is going to be not only like a very scoped issue, but also a feature. So we'll see how it goes. Just something that we are exploring, and it looks very good. And also the Google Summer of Code, it's entering into the final phase, I believe. At this point in time, we're probably waiting for Google to report us how many slots we got, and in a few weeks probably start working with the people assigned to the projects. And those are my updates. And then we can move to the talk. So it's my pleasure to introduce Antar Mazumder. Antar is a software engineer for dedicated to machine learning applications in FringeCore in Bangladesh, and the title of his talk is RoSE Terrain Generator (RTG) monocular depth-based synthetic DEM generation. So we're gonna see how to produce probably worlds, I believe, potentially in different planets with this technique. So Antar, whenever you're ready, it's all yours.
Thanks, Carlos. Am I audible?
Yes, you are.
Okay, so I'm gonna share my screen now. Is the screen visible now?
Yes.
Okay. So hi guys, thanks for the invite. Really happy to be here today. So I'm going to take you through a little script that I developed. I named it RTG or RoSE Terrain Generator, and we'll go through the details as I go. So just for the formality's sake, these are the topics I'm going to cover. First of all, I'm going to brag about myself a little bit more, and then we'll go through some basics about DEMs so that we are on the same page. And then we'll dive into RTG from a high-level overview, eventually breaking them down into low-level details. We'll also see how to convert the mesh in a format that is accepted into Gazebo. And we'll jump into pictures. Actually, we'll jump into two pictures. We'll also discuss about the pros and cons and the possibility about a version 2 of the script. And finally, we'll discuss about the details in the Q&A session. So first question, who is this guy? So my name is Antar Mazumder. That's the O sound from automobile. And I'm a mechatronics engineering major from Russian University of Engineering and Technology. I graduated in 2023. And I'm currently employed as a software engineer specialized in machine learning applications, especially computer vision applications at a software company named FringeCore in Bangladesh. So I have penned some papers. Most of them are around robot perception, digital twins, robot path planning, and I've also explored in other domains such as embedded AI and robotic exoskeleton. So that's about me. And now, before diving into the details, let us clear our basics. So what is a DEM? So DEM stands for Digital Elevation Model, and some even call it Digital Elevation Map. The later name is more familiar to me because that's the term I usually use in my lab. And so it is basically a 3D map of your terrain. So it has the elevation profile in a 3D environment, and each pixel or each grid represents the elevation in that location. So there is also a 2D version of it, but that is not actually called, you say, model. That is more known as the elevation profile, so to speak. And there are two types of DEMs. The first one is DTM, which I am addressing, which is digital terrain model, which doesn't have the features like vegetation or other buildings and so on and so forth. And there is another version of it known as the digital surface model or DSM. And in that case, we are going to consider multi-view angles. So in that case, we have to follow methods like master slam, Gaussian splat, or the Facebook's BGGT, if you're interested. So DEMs are usually created using satellite imagery, using LiDAR or radar techniques. And that's about DEMs. So another question is why we need DEMs. So there are many applications of DEMs, especially in geoscience applications, but in robotics, it is mostly used around the SLAM stuff. So SLAM means simultaneous localization and mapping. So it is basically map, and you use it as a general 3D map. So you have applications such as terrain mapping, and now that you have the map, you can localize your robot, you can navigate around obstacles and do the path planning algorithms and policy developments in a virtual environment or a digital twin. So my research is mostly concerned around digital twins. So that's the application I use to create virtual test beds. And to be more precise about the application, I can mention two very specific examples. The first one is used by NASA JPL in one of their Mars rovers. So they use a technique called Horizon 8. So what it does is it has a DEM, that is a 3D map of your landing site, and it kind of slices it up into 2D projections. And then uh, and it has a database of the horizon profiles, and it kind of matches that horizon to the DEM's horizon. And by using that, it can orient itself or localize itself in GPS denied environments. Because in environments like Mars or Moon, we don't have GPS satellites. Another application which was developed in my lab. So the name RoSE comes from my lab. I am If all goes well, I'm going to start my PhD at the RoSE lab at Colorado School of Mines. So RoSE stands for Robotic Space Exploration, hence the name RoSE Terrain Generator. So my lab mates devise the system where they take the DEMs and they run extensive simulations to find the best optimal traversal policy that uses least effort but gets most of the information. So these are some very precise examples of using DEMs. Now, the elephant in the room is RTG. So in very short, it takes you 2D image and gives you a terrain where you can simulate your robot. So as I previously mentioned, RTG stands for RoSE Terrain Generator, where RoSE stands for Robotic Space Exploration. And it is a Python script, but it is not a standalone script. That is, it doesn't work on its own. You have to place it in a specific folder. In my case, in the main version, it was in the root directory of the depth anything v2 repository. And in a newer version that I have developed in the beta script section, now available in the dev branch of the repository, I am using Apple's Dev Pro. So you have to place the script in that designated locations. The more details are in the repository. Don't worry about that now. So to get through the pros and cons in very short now, so it preserves the relative features. So for craters, you get craters. For hills, you get hills, and so on and so forth. And the most important thing is you get something when you have nothing. We'll come about the details in the later sections, but it also has some drawbacks because it is a purely monocular based depth estimation. It depends on the presence of light. So it can get noisy or give false readings when there is adequate absence of light. And it also struggles with estimating terrain scale, especially in astronomical distances, because the models were not trained for such long distances. We'll come to that later as well. So the question now is why RTG? So let's say Moon and Mars are two of the most uh, concentrated celestial bodies that we have been set our eyes for a while, and both of them have their own reconnaissance orbiters. So these are satellites equipped with very sophisticated depth sensors that can scan for kilometers. So they have a very vast range. But what about let's consider a terrain or a celestial body that we don't have a reconnaissance orbiter assigned to it. What we are going to do then? And there is also the question of payload. If we are equipping more depth sensors, the payload increases, and also the computational load. And if we have limitations such that we can only set a very lightweight satellite, where we cannot afford to put expensive or heavy depth sensors, we can do something like RTG, where we put a high resolution camera and then we take the feed, get the terrain, simulate our rovers in a simulated environment and send them in later missions. So that's another application of RTG as well. So before we dive into details, I'm going to talk very short about the backbone, the depth anything V2 model. So basically what happened, they had a physics simulator that labeled the distances very precisely. And we trained a very large Dino V2 model, which is a vision transformer model, just using those synthetic data. And then we use the teacher model to label more and more images. And using those more and more synthetic data, we trained a much smaller model, another Dino V2 smaller model. And then using some augmentation such as cut mix augmentation and semantic assisted perception, the smaller model became more robust than the teacher model, which is a rare phenomenon. That's why love this paper very much. So things to consider here is this takes a 2D image as input and returns a relative depth. So it is not actually giving you the actual depth because it's a monocular depth estimation based system. It is giving you a relative depth, or you can say an intensity map of depth intensity. So it is robust. It is zero. It gives you zero shot predictions, but it also struggles with depth scale estimation, especially at astronomical distances. So now a very high level overview RTG what we are going to do here. We're going to take an RGB image and we're going to infer using depth anything V2 to get a depth map. Then we're going to use a back projection, which is a method in pinhole camera systems to get a raw point cloud. And then we're going to do some post-processing such as outlier removal, voxel downsampling, normal estimation, all those stuff. And then we're going to wrap around a sheet around it, which is known as a process called Poisson surface reconstruction method. And that's going to give us a primary mesh. And after that, we're going to post-process it further in a software called Mesh Lab, which and wrap it around an SDF file to export into Gazebo. That's the basic idea. So it all starts from the config file. I could go line by line in the code, but that's not optimal, I think, given the time. So I'm going to go through the main parts here. So first, in the config file, there are, I would say, 4 important parameters. The first one, as I previously mentioned, it uses Dino V2. So it's a vision transformer based model. So I'm using vision transformer base model as an encoder. And the most important hyperparameter here is the max depth. So as I previously mentioned, depth anything V2 is going to give you a relative depth map uh, on each pixel. And by giving a max depth hyperparameter, we are setting the max depth as the value we are assigning here. And all the other relative depths are scaled according to this max depth. So I did a quick Google search, and according to that search, Martian craters has a maximum depth recorded of around 2.5 kilometers. So I put 2,500 units or 2,500 meters in Gazebo. And there are also other intrinsic parameters, such as the focal length around x-axis and y-axis. So I didn't have the exact parameters of the camera intrinsic used in that image. So I put 470 arbitrarily. But there are workarounds to get the actual stuff. That's something I'm going to discuss when I go to the version 2 section. And then we have voxel downsampling. So that's basically divides the entire mesh into cubes. The lesser the size of the cube, the more details you are going to get, but the file size will also increase and also in the computational load. And I have also left some options for post-processing, such as outlier removal. So it all starts with inference, as I previously mentioned. So we pass in an image to the depth anything model, and using the infer function, we get the depth map. So if we go into the background, this is something we are going to get. This is actually the output from the code. So as you can see, I'm passing an image size of 724 by 539. And after generating a basic depth map, we are getting a depth range between 4.45 to 7.12, which is not accurate at all because the MRO takes pictures from around 50 kilometers of the surface. So it is not near even close to the actual distance. So as you can see, after doing the scaling, the depth range increases. Now it is between 1717 to some, as the max that I assigned, 2,500 units. And I'm also doing something called gamma corrections. It is not mandatory, but it uh, allows you to adjust the contrast better. I'm using a value between less than 1. So the objects which are closer are more prominent. They have less darkness. So they are more visible to us. So anyway, moving on. And then we convert them into point cloud. So this is a pinhole camera projection method. It was actually used in the depth anything V2. There is a script called depth to point cloud. in that they use this process, a pinhole camera method, which I have adopted. So we first take the x as the width, y as the height, and do some basic calculations here. And this is where the hyperparameters come in. As you can see, we are dividing the results by the focal length x. So this will estimate the x and y coordinates. And the z is basically the scale prediction, which I got from the previous snippet. And here I am setting a condition so that very far points, basically very depthy points, which are less than 10% of the max height, are removed. So we get some outlier rejection right out of the box. And then we stack them with color information, and using Open3D, we stack them into a raw point cloud. So the next is some post-processing. So we are first removing some outliers. So it is a KD tree-based method. So basically, for each point, we are taking 20 neighbors, right? And then we are getting the average distance of those points from the target point. And any point that is more than 2 standard deviation away from the average distance is considered an outlier and is removed. So it is a very neat trick. So after outlier removal, I am doing some voxel downsampling process. So basically, as I previously mentioned, I am reducing the mesh into cubes so that the file size kind of drops from like 700 megabytes to around 5 megabytes. So depending on the hyperparameter you set, it will go down drastically or even or less, depending on however you prefer. So next very important thing is estimating the normals around the surface. So I am taking like 30 points and drawing a surface on those points. And then we are I'm setting a normal vector on that is perpendicular to the surface. So it allows us to estimate the curvature and the depth of the mesh, not the point cloud of the mesh. So it makes us ready to use the next algorithm, which is known as Poisson surface reconstruction. It is a big course. I have skipped it here. So basically what it does is it wraps around a sheet around the estimated normals. So you get a mesh, basically. It's very high level overview, I know, but that's what it's doing basically. So then it returns the mesh, which is saved in your designated format. In my case, it was PLY and OBG. OBG can be directly exported into Isaac Sim, but for Gazebo, we have to do some post-processing. So the mesh itself is not ready out of the box. We have to do some further reprocessing, and that's where MeshLab comes in. So MeshLab is quite light. That's why I used it. But if you want something more robust, you can go for Blender. It's up to you. So first you have to import the mesh, and then we have to, orient the mesh. So as you can see, the principal axis is kind of below the mesh, which is not something we want. We want the principal axis to be at the center of our mesh, so to speak. So I'm doing that, and then I'm assigning textures and exporting that mesh into a DAE file or Collada file, you might say, which is accepted into Gazebo. And then finally, I am using custom SDF files to create my preferred environment. We'll come to that when I show you the jump into the picture part. And then you have a terrain that is ready for Gazebo import and ready for simulation. So now is the exciting part, I guess, where we're going to jump into the picture. Here you can see this is the image of a Martian terrain, right? So this is the 2D image of the terrain, and now we're going to jump into it. And all the information we have is this picture alone, nothing else. So let's see. I'm going to fast forward it around 10 seconds. So I dropped a ball on the terrain, so you can see the dynamics and the collisions and stuff. So let's see. By the way, I scaled it down, so it is 0.1% of the total mesh generated. So it is looking quite small, but the actual thing is quite big. As you can see, the ball interacts with the terrain just like you would expect your robot to do when it is a wheel robot or something. So that's about it. You have a pictures, and now you can explore Martian surface at least digitally just by using a picture. So I have used a very thin mesh, but you can, if you want, you can fill it up, like have a platform or something. It's up to you. But that just increases the file size, so I skip that part. I think it falls down eventually. Yeah, it falls down. So another thing to notice that you might see there are no rocks or ridges in the map. That's because in the satellite imagery, we don't have information about those as well. So if you want rocks or other formations, yeah, thanks. I sleep with Interstellar tune playing in the background, by the way, just so you know. So anyway, so if you have, like if you want rocks or other ridges, you can put them using a software like Blender into that mesh, but it gives you a very realistic base. And instead of generating a fully 3D synthetic terrain on your own, so it gives you a very solid base that is actually based on the target terrain. And this is another example of moon this time. So here I added a dummy terrain, which I dropped. This is a sped up video, by the way, but it drops down very slowly because moon has less gravitational attraction. Yeah, that's your like moon surface. I didn't assign any texture here, but that's up to you. You can use texture, but if you are good with the texture, that's fine for you as well. So those are the two examples. Now, what are the pros and cons? So just like I mentioned, it's a monocular depth estimation based approach. So we don't have access to actual depth. So that's the limitation. We are estimating depth. So and the model we are using to estimate those depth is not actually trained on astronomical depths itself. So we have to do some post processing here. And even after post processing, we might not get the actual scale, which might be an issue if you want very high fidelity virtual test beds. But if you are looking for a terrain that is based on the target terrain, the realistic terrain, and just want the features. So you want the craters to be craters, the hills to be hills, some big rocks to be rocks. This is your go-to script, I would say, for me at least. So as I said, it preserves the relative features and it has the potential to reduce your payload in space missions where we cannot afford expensive depth sensors. And the most important part is something is better than nothing. When you have no depth cameras, depth sensors, you can at least use your camera to get some terrain information that you can use in your virtual testbed and simulate your rover and develop a high fidelity algorithm or policy, whatever you call it. So that's the pros and cons. And so do I have a version 2? I actually have two beta scripts available right now. So they are, if you go into my GitHub, there is the main branch, and in the dev branch, voila, there are two more scripts. One is RTG v2, which is based on depth anything v2 but enhanced. And there is another one called RTG scale, which is based on Apple's Depth Pro, which gives direct metric depth, but it also automatically detects the camera intrinsics. That's why I'm using it here. So anyway, moving into the main part again. So RTG v2, this was generated using RTG v2, by the way, and as you can see, it has improvements. It has noticeable improvements, especially with filling the holes. So, and for RTG scale, that since it can actually detect the camera intrinsic parameters, that is the focal X and focal Y and other parameters. So we have to do less post processing, if that makes sense. So in my experiments, I took a 500 kilometer DEM, and the DEM I got was around 700 kilometers. It is around 200 kilometers off, I know, But considering astronomical distances and the absence of depth cameras, it's kind of decent, I would say. It's not the most impressive, but we are somewhere around there, and we can always scale it down. So it's up to you. And that's about it. That's all. And let's move into the Q&A section. So I am just learning. I'm no expert, and I made this the first primary script during a lunchtime. So yeah, that's a messy code, but let's go with it for now, I guess.
Thanks, Antar. Yeah, thanks a lot for the presentation and for the
Thank you.
project. It's pretty cool. Questions for Antar. Tharin, you have a question, or you might be clapping. Yeah. Okay. Well, I have a few questions. So I know that this is not the goal of your tool. I know on Earth, for example, right? We have very high fidelity DEMs. But out of curiosity, did you try to generate like a DEM from the Earth, from an existing image, just to compare the generated DEM by your tool with an existing DEM, and see what happens?
So we have a lunar testbed in our lab, lunar regolith testbed it is called.
Mm-hmm.
So I did some side-by-side comparison against a depth sensor, actual depth sensors, the real sense to be exact, and I found that given the camera intrinsics for very small objects, the deviations is around 7 centimeters in average for very small, small range objects. But when you increase the distance, the deviations kind of, add up, and then you get kind of larger distortions. But considering the astronomical scales, it is still doable, and we have some sense about the dimensions of our celestial body, so we can always scale it down if we want. Basically, consider a very hypothetical scenario. Let's say we are exploring a very uncharted terrain, and you have the rover. What can I show? Let's say this is our rover, right? So we have a lander attached to the rover, and we don't have any DEMs of that uncharted territory. So just before we land, we can take a snapshot of the terrain we are going to explore, get a quick DEM, send it to the rover. It does some onboard calculations to find the optimal traversal policy, and then it sets its waypoints around the DEMs using its depth sensors. So in such cases, we are not actually interested about the distortions. We can always compensate that using RANSEC or other alignment algorithms that will sort it out. Like if this is the hill, this might be a hill from that DEM, if I can make sense. So in that case, this is quite useful in my experience.
Yep. That sounds great, and I know that the goal is just not to generate a high fidelity DEM, especially on Earth where we have better tools. But yeah,
Yes.
it's out of curiosity. And another question is, I know that the end result, as you mentioned, is a mesh, right? And
Yes.
I can imagine that maybe you're doing this because it's a portable end result, maybe that you can move around and you can reuse in different simulators. But again,
Sure.
out of curiosity, did you consider producing, instead of a mesh, a height map? Maybe for
I did.
efficiency reasons or something like this?
I haven't worked around that yet, but since you mentioned, that should be interesting to explore. When I move to mines, I'm into transition period, so I'm getting very little time to do my experiments. But yeah, that's a nice idea, I guess.
Yep. Thank you. Other questions for Antar? Ian?
Yeah, so thanks. That was a great presentation. I saw one of the cons is shadows. I may have missed it. How, like in some cases, they are like huge. When the sun is at a low angle, the moon, for example, it has really long shadows. Did you mention how to cope with this, removing shadows to get a better depth map?
So there are two techniques I'm using. The first one is, first of all, let me go to the moon section. Here. So this itself is kind of an optical illusion. So I showed it to some of my colleagues, and they think that these are extrusions, not craters. You know. So if you look at them long enough, sometimes you can see them as extrusions, sometimes you can see them as craters, and that's the problem with shadow. So based on how the light is projected and how the shadow is generated, you may get different results, and that's one of its limitations. But so far, according to my experiments, it worked fairly well, right? That's the first thing. And in many cases, when you are considering a reconnaissance orbiter, they usually take perpendicular shots where they are right on top of the terrain to get the best results to use this system. So in that case, you are getting less shadow pollution in a sense. And the other thing I'm using is something called uh, gamma correction, I think. Yeah, something called gamma correction. So very straightforward approach. See, you can see this is the not corrected mesh. This is a wonderful presentation. And now corrected, the mesh looks much better. The contrast, the shadows are better. So that's another thing I was using. And as I mentioned, it is not mandatory. But if you don't use gamma corrections, your depth map will feel a little bit bland. You know, it will have less range of shadows. So that's another thing to consider as well. I hope that answered your question.
Okay, yeah, I guess you're making the darker pixel brighter, so the shadowed region
Yeah,
brighter.
I am making the nearby details less dark, so they are more prominent compared to the further objects in the mesh, if that makes sense.
Okay, thanks.
Thank you.
Cool.
Yeah, just a quick thing, going back a little bit to the terrain mesh itself. I posted a link in chat to the Gazebo model repository. We did a lot of work on open robotics projects with terrain, and there's a lot of good examples there of worlds where we've used height map based terrain instead of meshes. So just something you might look into to kind of get you started on that path if that's something you're interested in.
Sure.
Any other questions? All right, then let's thank again Antar. Thanks for the presentation.
Thanks, guys.
Yeah, you're more than welcome to join anytime, Antar. And any other general question, any other Gazebo topics to bring up? We have some time, so we can leave early, but if anybody wants to discuss anything about Gazebo, we have some time. All right. Once, twice. Okay, so I think we're good to go. So thanks everybody for tuning in, and we'll see each other next month. Have a good day, everybody.